The brightest point of light in your evening sky is not a star. It is a planet, almost exactly the size of the world you are standing on, made of the same rock, born beside us from the same cloud, around the same sun. For most of human history, people looked at that calm silver light and assumed it was the gentlest world out there, a warmer, wetter sister to Earth, the obvious place we would go when we finally left home. They were wrong in the most complete way it is possible to be wrong. That bright twin is the hottest planet in the solar system, hot enough to melt lead from pole to pole, sealed under an atmosphere 90 times heavier than the air you are breathing right now. And the most unsettling part is not how different that world is from ours. It is how nearly identical the two of them began, and how short the walk turned out to be from a living planet to a dead one. Get comfortable. Hit subscribe if you're new here, because by the end of this, that quiet light in the west is going to look less like a neighbor and more like a photograph of our own distant future. Now, let's slowly ease into this. Part 1. The twin we expected. For almost the whole of human history, Venus was the friendly one. It is the brightest thing in our sky, after the sun and the moon, a single clean point of silver-white light that hangs low after sunset or rises ahead of the dawn, steady and calm where the stars flicker. People have watched it for as long as there have been people. They named it after goddesses of love and beauty because it was lovely and because it seemed gentle. The morning star and the evening star, once thought to be two different objects, turned out to be the same quiet light, making the same patient circuit, and for thousands of years that light carried no menace at all. If any world out there was going to be a second home, a softer version of our own, surely it was that one. The reasoning behind that comfort was not foolish. It was, in fact, almost good science. Venus is the planet that comes closest to Earth, sometimes swinging to within about 25 million miles of us, nearer than any other world ever gets. It is nearly the same size, just a little smaller across than Earth, and nearly the same mass, and made of the same kind of rock, born in the same part of the same cloud of gas and dust, around the same young sun, about 4.5 billion years ago. By every measurement anyone could take from a distance, Venus and Earth were a matched pair. Twins. And so the natural assumption, the one almost everyone made, was that a twin of Earth would be a twin in the ways that matter. A little warmer, perhaps, being closer to the sun, but fundamentally a sister, fundamentally alive. The clouds only deepen the dream. Every other planet shows you its face. Mars shows its red deserts, Jupiter its banded storms, the moon its craters. Venus shows you nothing. It is wrapped, pole to pole, in an unbroken layer of pale cloud that never parts, never thins, never offers a single gap to look through. For centuries, no telescope on Earth, no matter how good, could see one feature of the actual surface. And when you cannot see something, you fill the silence with hope. Those clouds, people reasoned, must be water clouds, like ours. And if there were clouds, there was weather. And if there was weather, there was rain. And under the rain, beneath that soft white veil, there might be warm, shallow seas, dripping jungles, ferns and swamps, and the slow churn of a younger, wetter earth still finding its feet. That picture was everywhere, and it lasted a remarkably long time. Well into the 20th century, serious scientists and popular writers alike imagined Venus as a steaming primeval world, a carboniferous garden. The planet Earth had been hundreds of millions of years ago before it cooled and settled. Science fiction sent explorers into Venusian rainforests and oceans without blinking. The idea was so reasonable, so emotionally satisfying, that almost no one questioned the basic shape of it. The bright twin in the evening sky was the place we would go when we finally left home. It was the obvious candidate, the gentle option, the world that looked the most like us. And every single piece of that was wrong. Not slightly wrong, not wrong in the details, but wrong in the way a thing can be wrong when reality has decided to teach you a lesson. The clouds are not made of water. They are made of sulfuric acid. The surface beneath them is not a warm, shallow sea, but the hottest solid ground in the entire solar system, hot enough to melt lead, hot enough that metal would slump and run. The gentle twin is, by a wide margin, the most lethal planet we know of, a place that would kill an unprotected human being in 3 separate ways at once, before the body even had time to register which insult arrived first. The morning star, the symbol of love, the soft option, turned out to be a furnace with a beautiful lid. I want you to sit with how complete that reversal is, because it is the whole reason this story matters. This was not a far-off, alien world that we expected to be strange and found to be strange. This was the world we expected to be most like home. It had the best resume in the solar system. Same size, same mass, same materials, same starting line, right next door. If you had asked any reasonable person 300 years ago to bet on which other planet was most likely to be a second Earth, they would have pointed without hesitation at that bright, steady light, and they would have had every good reason to. And they would have lost the bet more badly than almost any bet in the history of science. So the question stops being a curiosity and becomes something closer to a warning. 2 planets began as twins. They were handed, as far as we can tell, the same starting hand, the same rough size, the same rough chemistry, the same young sun, separated by a gap that is, on the scale of the cosmos, almost nothing at all. And one of them became the only living world we have ever found, draped in oceans and forests and the soft machinery of a biosphere, while the other became a sealed oven where nothing we know of could survive for a heartbeat. That is not a difference you can wave away as bad luck. Something happened to Venus, something physical, something specific, something that turned a possible second Earth into a corpse. And whatever it was, it is worth understanding very precisely, because it did not happen to a distant stranger. It happened to our twin. There is a colder thought folded inside that one, and we will come back to it again and again tonight, so let me just set it down gently here at the start. If Venus and Earth truly began the same, then the thing that destroyed Venus was not some flaw Venus was born with and Earth was spared. It was a process, a sequence of physical steps that any world of the right size, with the right chemistry, sitting a little too close to its star, can be walked through. And if it is a process rather than an accident, then the obvious and uncomfortable question is whether that same process has anything to say about Earth. Not as a metaphor, and not as a scare. As physics, the title of this is that Venus is what Earth will become, and that it is already starting. And by the end of tonight, I want you to understand exactly how much of that is true, where the line between the real warning and the false alarm actually falls, and why the honest version of the story is somehow both more reassuring and more sobering than the headline. It is worth knowing how stubborn the gentle twin dream actually was, because the length of time we clung to it is itself a measure of how badly Venus fooled us. The Swedish scientist Svante Arrhenius, the same man who first worked out the basic mathematics of the greenhouse effect more than a century ago, imagined Venus as a warm, humid, dripping world, a place of swamps and luxuriant growth. Writers followed the scientists, filling Venus with oceans and rainforests and reptilian life, because the science of the day gave them every permission to. The unbroken white clouds were treated as proof of a wet world, since on Earth, white clouds mean water, and no one could see through them to learn otherwise. For decade after decade, the most reasonable reading of the evidence pointed to a sister world, and the dream held because nothing yet contradicted it. The first real crack did not come from a spacecraft at all. It came in the 1950s and early 1960s, when astronomers began pointing radio telescopes at Venus and measuring the faint microwave radiation coming off it. That radiation carried a temperature, and the temperature it implied was not the mild warmth of a swamp world. It was hundreds of degrees, far too hot for any ocean, far too hot for any swamp, far too hot for anything we would call life. At first, many scientists refused to believe the surface itself could be that hot and looked for other explanations, because the gentle twin was simply too reasonable to give up easily. But the number would not go away, and when the first spacecraft finally reached Venus and measured it directly, the radio telescopes were vindicated. The garden was a fiction. The truth was an oven, and we had been gazing fondly at it for centuries, calling it our sister, never suspecting what the clouds were hiding. But before any of that, before we can talk about why Venus died or what it means for us, we have to actually go there. We have to get underneath those clouds and stand on the ground that no human eye saw for the entire span of human history, right up until a single afternoon a few decades ago, when a small, doomed machine sent home the first pictures from inside the furnace and then fell silent forever. To understand what Venus became, you have to meet it the way we first really met it, not as a point of light, but as a place. And the story of how we got down through those clouds and onto that surface is one of the strangest and most quietly heroic chapters in the whole history of exploration. Part 2. The machines that died on the surface. The first machines we sent toward Venus did not survive what they found, and the way they failed told us more than their builders wanted to know. In the 1960s, both the United States and the Soviet Union began throwing spacecraft at Venus, and at first almost nothing worked. Probes went silent on the way. Probes sailed past and saw little. The Soviet Union, in particular, became almost obsessed with Venus, pouring mission after mission into a program called Venera, the Russian word for Venus, and the early Venera probes met the planet and simply stopped existing. They were designed by people who still half believed in the warm twin, the gentle sister, and they were built to handle a world that turned out not to be there. The trouble was that the engineers kept badly underestimating the place. The first Venera craft that tried to descend into the atmosphere were built to withstand pressures a few times that of Earth's surface, because that seemed like a generous margin. Venus crushed them long before they reached the ground. They were flattened in the upper atmosphere, like paper cups at the bottom of a swimming pool, their signals cutting out while they were still falling. Each failure sent the same brutal message back up the chain. Whatever is down there, it is far worse than you imagined. Build it stronger. Build it like a submarine. Build it to be crushed and cooked and keep working anyway, at least for a little while. So that is what they did. The later Venera landers were among the toughest machines human beings have ever constructed. They were squat metal spheres, pressure vessels with thick walls, engineered to function not on a planet, but inside something closer to the depths of an ocean. The teams ran them through ground tests in chambers that simulated the heat and the weight of the Venusian air, and they reinforced them again and again, knowing the whole time that no matter what they did, the planet would win. These were not machines meant to last. They were machines meant to survive long enough to look around once and tell us what was there before the environment tore them apart. And in 1970, one of them made it. Venera 7 became the first spacecraft in history to make a soft landing on the surface of another planet and send a signal back. It was a faint, garbled transmission, weaker than expected, because the probe had likely toppled over on impact, but it was real, and it lasted about 23 minutes before it died. 23 minutes. That was humanity's first message from the ground of another world, and it came from the surface of the planet we had spent centuries imagining as a gentle garden. The data confirmed the nightmare the earlier failures had hinted at. The pressure at the surface was about 90 times that of Earth. The temperature was hot enough to destroy the craft. The garden was an oven, and now we had stood in it for 23 minutes through the body of a dying machine. The Soviets did not stop. They kept going, and they kept getting better at it, and a few years later, they did something that still feels almost impossible when you really consider it. In 1975, Venera 9 landed and returned the first photograph ever taken from the surface of another planet, a single grainy black and white image of a slope of flat, broken rocks running off toward a startlingly close horizon. Human beings had never seen the ground of another world with their own instruments before that moment. And the ground we saw first was the ground of the furnace. Then, in 1982, came the landers that returned the images people still find hard to believe are real. The ones in color, from Venera 13, the machine that became the surface survival record holder and has never been beaten. Picture what that machine actually did. Venera 13 falls through more than 30 miles of acid cloud and thickening, superheated air, slowed by parachutes, and then by the sheer density of the atmosphere itself, until it settles onto a flat plain of slabby volcanic rock under a sky no human had ever stood beneath. The light around it is strange, a dim, sourceless orange, the color of the sky filtered through that endless cloud, with no sun visible, no shadows, just a uniform amber glow, as if the whole world were lit from inside a dirty lamp. A small spring-loaded arm swings down, and a drill bites into the rock to sample the soil, grinding out the chemistry of a place no one will ever touch. The lens cap pops off, and the camera begins to turn, sweeping slowly across a plain of cracked stone slabs that runs to a horizon that feels too near because the thick air bends the light. There is no wind to speak of at the surface, just a heavy, sluggish stillness. The temperature outside is about 465 degrees Celsius. The pressure is the weight of nearly a kilometre of seawater pressing on every surface. And the little machine keeps working, taking its pictures, running its tests, sending it all home, for 127 minutes before the heat finally reaches its electronics and it goes silent forever. That is the longest any machine has ever survived on the surface of Venus, a little over 2 hours. We have rovers that have crawled across Mars for years, machines on the red planet that have outlived their own mission plans by more than a decade. On Venus, our best effort, our toughest submarine of a lander, bought us 127 minutes before the planet killed it. No spacecraft has operated on that surface for longer in all the years since. The handful of images those Venera landers sent back, those dim orange photographs of broken rock under a sourceless glow, are still, to this day, essentially the only pictures we possess of what it actually looks like to stand on the ground of Venus. We have better maps of the surface, made by radar peering through the clouds from orbit. But for the actual view, the thing your eyes would see, we have a few minutes of footage from machines built to die, and nothing else. There is something worth pausing on in that fact, because it reframes the entire planet. We tend to think of Venus as well explored, a checked box, the second planet, done. It is not. It is one of the least accessible solid surfaces in the solar system, a place so hostile that the sum total of our direct experience of its ground amounts to a few hours of borrowed time across the entire space age. The reason is not distance. Venus is close, the easiest planet to reach in terms of getting a craft there. The reason is the surface itself. It does not permit visitors. It allows brief witnesses, and then it erases them. And every one of those witnesses came home with the same testimony, written in the way they died. This is a world that began like ours, and became something that destroys, in under 3 hours, the most durable machines we know how to build. It is worth dwelling on the engineering, because the ingenuity is part of what makes the failure so haunting. To give the landers even their 2 hours, the Soviet teams resorted to tricks that sound almost desperate. They chilled the interiors of the probes far below freezing before arrival, so the machines would begin their descent as cold as possible and have further to climb before the heat destroyed them, the way you might pre-chill a drink so it lasts a little longer in the sun. They packed the electronics into thick pressure spheres and cushioned them, sealed them, insulated them, and still the planet won every time, just a little more slowly with each improvement. Building a lander for Venus was not like building a lander for the Moon or Mars, where the main enemy is the cold and the vacuum. It was like building something to be lowered into the firebox of a furnace and asked to keep taking photographs as it cooked. The wonder is not that the landers died so quickly. The wonder is that they worked at all. And consider what it means that those few images remain, to this day, essentially the entire visual record of the surface. We have driven rovers across Mars for years on end, accumulating hundreds of thousands of photographs, watching the seasons turn and the dust devils pass. We have machines still trundling across the red planet right now, sending home pictures by the thousand. Of the surface of Venus, the planet that is closer to us and more like us, we have a handful of dim orange frames from the early 1980s and nothing newer. Not one photograph has been taken from the surface of Venus in over 40 years, because nothing we have sent since has been able to survive long enough to take one. In a space age full of triumph, the ground of our nearest neighbour remains one of the least seen places we have ever reached, witnessed only through the eyes of machines that were dying as they looked. So we have stood on Venus, in a sense, for a total of a few hours through the eyes of the dying. We have the numbers those machines sent back, and the numbers are where the real horror lives, because they are not just large, they are wrong in a way that should not be possible. The next thing we have to do is look hard at those numbers, the temperature and the pressure, and one comparison in particular that, once you understand it, quietly demolishes the most basic assumption you have ever held about why some worlds are hot and others are cold. Because the most shocking thing about the heat of Venus is not how high it is where it comes from. Part 3. The numbers that should not be. The surface temperature of Venus is about 465 degrees Celsius, and the first thing to understand about that number is how strangely even it is. On Earth, temperature is a patchwork. The poles are frozen while the tropics swelter. The day side is warm while the night side cools. A desert noon is brutal, while the same desert before dawn can be cold enough to need a coat. Venus has almost none of that variation. It is about 465 degrees at the equator and about 465 degrees at the poles. It is that hot on the side facing the sun and very nearly that hot on the side facing away, in the middle of a night that lasts for weeks. The entire planet, top to bottom, day and night, sits at a single roasting temperature, held there by an atmosphere so thick and so good at moving heat around that no part of the surface ever gets a break. To put that temperature in human terms, it is hot enough to melt lead. Lead becomes liquid at about 327 degrees Celsius, and Venus is well past that, so a block of lead set on the ground would slump and spread like butter on a warm counter. Tin and zinc would melt too. The surface is not metaphorically an oven. It is literally hotter than the self-cleaning cycle of the oven in your kitchen, by a wide margin, everywhere, all the time, with no door to open and no way to cool down. And the heat is only the first of 3 ways the planet would kill you. The second is the pressure. The air at the surface of Venus presses down at about 92 times the pressure at sea level on Earth. That is roughly the pressure you would feel if you swam down to about 3,000 feet beneath the ocean, far below the crush depth of most submarines. It is not a breeze you would feel, it is a weight, a dense, syrupy heaviness that would compress you instantly. And the third insult, almost an afterthought next to the first 2, is that the clouds and hazes are laced with sulfuric acid, crushed, cooked, and dissolved, all at once, in an atmosphere that is about 96.5% carbon dioxide and almost entirely unbreathable. That is the planet we once imagined as a garden. Now, I want to hand you the single fact that, for me, is the most quietly devastating number in all of planetary science, because it overturns something you have believed since you were a child. You have always known, in a loose, intuitive way, that planets close to the Sun are hot and planets far from the Sun are cold. It is one of the first facts anyone learns about the solar system. Mercury, closest to the Sun, is scorched. Pluto, far out in the dark, is frozen. The Sun is the fire, and the closer you sit to a fire, the warmer you are. That rule feels as solid as anything in science, and it is almost the first thing Venus takes away from you. Here is the problem. Venus is not the closest planet to the Sun. Mercury is. Venus orbits nearly twice as far out from the Sun as Mercury does, and by the childhood rule, that should make Venus noticeably cooler than its inner neighbor. But Venus is not cooler than Mercury. Venus is hotter, considerably hotter, and far more relentlessly. Mercury, sitting right up against the Sun with almost no atmosphere, reaches about 430 degrees Celsius at noon on its day side, which is blistering. But Mercury has no air to hold that heat, so the moment the Sun goes down, all of that warmth radiates straight back out into space, and the night side of Mercury plunges to about minus 180 degrees Celsius. Mercury swings wildly between a scorching day and a hard frozen night because it has nothing to keep the heat in. Venus, nearly twice as far away, sits at a steady 465, hotter than Mercury's hottest noon, and it holds that temperature through the entire weeks-long night without dropping. The farther planet is the hotter planet. The childhood rule is broken. Once you really absorb that, the explanation becomes the most important idea in this entire story, so let me state it as plainly as I can. The temperature of a planet's surface is not set primarily by its distance from the Sun. It is set by its atmosphere. Distance gets a vote, but the air casts the deciding ballot. Mercury is closer and colder at night because it has no blanket. Venus is farther and hotter always because it is wrapped in the thickest, heaviest blanket of greenhouse gas in the solar system. The sunlight that filters down through those clouds warms the surface, and the surface tries to radiate that warmth back out as infrared heat, the way a parking lot releases its warmth into the evening. But the carbon dioxide in the Venusian air catches that outgoing heat and throws it back down, over and over, trapping it, building it up, until the surface settles at a temperature where it can finally force enough heat through the blanket to balance what comes in. On Venus, that balance point is 465 degrees. You can put a number on how much work the blanket is doing, and the number is staggering. If Venus had no atmosphere at all, just bare rock at its distance from the Sun, its surface would settle at something in the range of a temperate afternoon, somewhere not far from the comfortable temperatures we live in, give or take. The atmosphere alone, the greenhouse effect alone, is responsible for raising the surface by roughly 500 degrees above where it would otherwise sit. 500 degrees of warming, produced not by the Sun being close, but by an invisible gas doing exactly the thing that same invisible gas does, in much smaller measure, in the air above your head right now. Venus is not hot because of where it is. Venus is hot because of what is in its sky. And that single correction, distance does not set the temperature, the air sets the temperature, is the hinge that the rest of tonight turns on. There is a detail about the air of Venus that helps you feel just how alien the surface really is, and it has to do with how the atmosphere behaves down there. The air at the bottom of the Venusian atmosphere is so dense and so hot that it stops acting like the thin gas we know and starts behaving like something between a gas and a liquid, a thick, soupy medium that would press against you almost like water. If you could somehow stand on the surface and survive, you would not feel a breeze. You would feel a heavy, syrupy resistance, the way you feel the water pushing back when you try to walk along the bottom of a swimming pool. Light would bend strangely through that dense air, lifting the horizon and curving distant features upward, so that the ground would seem to rise away from you in every direction, as if you were standing at the bottom of a shallow orange bowl. It is a place that does not just have extreme numbers. It is a place where the ordinary behavior of air and light and matter has been quietly bent into something you would not recognize. The uniformity of the heat is its own kind of strangeness, and it comes straight back to the blanket. On Earth, the difference between the equator and the poles is enormous. The difference between noon and midnight is real and felt, because our thin atmosphere cannot move heat around efficiently enough to erase those differences. Venus erases them completely. Its atmosphere is so thick and so active that it carries heat from the day side to the night side and from the equator to the poles almost perfectly, smoothing the entire planet to a single temperature. There is no cool place to retreat to on Venus, no shaded pole, no relief in the long night. The whole globe sits at one searing value, held there by the same heat-trapping, heat-spreading blanket that makes the planet hot in the first place. Even the sulfuric acid that falls from the high clouds never reaches the ground as rain. It evaporates back into vapor in the scorching air far above the surface, falling and vanishing, a rain that the heat will not let land. So hold that, because it reframes everything. The furnace is not a furnace because Venus drew a bad seat near the fire. Venus drew a seat near the fire, yes, a little closer than Earth, but the fire alone would have left it survivable. The furnace is a furnace because of its atmosphere, because of what that atmosphere is made of and how much of it there is, which means the real question is no longer, why is Venus so close to the Sun? The real question is, why does Venus have that monstrous atmosphere in the first place, and Earth does not, when the two planets started as twins? And the answer to that question is going to take us somewhere genuinely unsettling, because the difference between Earth's gentle sky and Venus's crushing one is far smaller and far more fragile than the gulf in their temperatures would ever lead you to believe. Part 4. The Twin Paradox. Let me lay the two planets side by side, the way you would compare two siblings, because the resemblance is the thing that makes the difference so disturbing. Venus is about 95% of Earth's diameter, very slightly smaller, close enough that from a distance you could mistake one for the other. Venus has about 81% of Earth's mass, so its gravity at the surface is about 9/10 of ours, a difference your body would barely notice. The two worlds are made of the same basic stuff, rock and metal in roughly the same proportions, an iron core wrapped in a rocky mantle wrapped in a thin crust. They formed at the same time, about 4.5 billion years ago, out of the same swirling disk of debris, around the same newborn sun, in neighbouring lanes of the same track. If you were drawing up a list of the two most similar large objects in the solar system, you would put Venus and Earth at the top without much argument. They are, by birth, twins, and the distances are not even that different. Earth orbits at a certain distance from the Sun, and Venus orbits at about 72% of that distance. Venus is closer, certainly, but not dramatically so. It is not in some wildly different region of the solar system. It is right next door, one lane in, receiving about twice the sunlight Earth gets, which sounds like a lot until you remember that doubling the sunlight, on its own, should not come remotely close to producing a 500-degree furnace. The extra sunlight Venus receives is real, and it matters, and we will see that it is the spark that lit the fuse. But it is not by itself the explanation. Two worlds, nearly the same size, nearly the same mass, made of nearly the same materials, sitting one lane apart around the same star. By every reasonable expectation, they should have turned out similar. Instead, one became the only living world we know, and the other became the most hostile surface in the solar system. That divergence is the core mystery, and the temptation is to explain it away as luck, as if Venus simply drew a bad card. But the more closely you look, the less it looks like luck, and the more it looks like a mechanism, a specific physical process that took two similar worlds and drove them to opposite ends. To see the mechanism, you have to look at the one number where Venus and Earth are not similar at all, the one place the twins are wildly, almost incomprehensibly different. It is not their size, or their mass, or their distance. It is their air. Earth's atmosphere is thin and breathable, about 78% nitrogen and 21% oxygen, pressing down at a pressure we evolved inside of and never think about. Venus's atmosphere is a crushing ocean of carbon dioxide, about 90 times more massive than ours, pressing down 92 times harder. That is where the twins parted ways. Everything else about them is nearly identical. The sky is where they became strangers. But here is the twist that turns the whole thing from a curiosity into something that should make the back of your neck prickle, and it is a fact most people have never heard. Earth is not actually short on carbon. Our planet contains a quantity of carbon broadly comparable to the amount Venus has. The carbon is here. We have just about as much of the raw ingredient for a Venusian sky as Venus does. The difference between the two worlds is not how much carbon each one owns. The difference is where that carbon is kept. On Venus, almost all of the carbon is in the air, loose as carbon dioxide, forming that 90 times thicker atmosphere and doing all 500 degrees of greenhouse work. On Earth, almost all of our carbon is locked away, buried, taken out of circulation. It is bound up in stone, in the enormous deposits of limestone and chalk and other carbonate rocks that make up entire mountain ranges and lie in thick layers across the floors of our oceans. It is dissolved in the seas. It is held in living things and in the fossilized remains of things that once lived. The white cliffs that ring some coastlines, the limestone that builds cathedrals, the chalk in a stick of classroom chalk, all of it is carbon that has been pulled out of Earth's air and filed away in solid rock over hundreds of millions of years. If you could somehow gather up all the carbon that is currently sealed inside Earth's rocks and seas and release it into the sky as carbon dioxide, our atmosphere would swell into something crushing and choking and hot, something far closer to the atmosphere of Venus than to the thin blue air we breathe. The ingredients for a Venus are already here. They are simply in the ground instead of in the sky. Let that reframe the whole comparison for you. Venus and Earth are not separated by some great difference in what they are made of. They are separated by a single question of bookkeeping, of where the carbon ended up. One planet kept its carbon in the air and cooked. The other planet buried its carbon in the ground and lived. And that turns the central mystery into something much sharper and much more uncomfortable than where did Venus get all that carbon dioxide. The real question is, why did Venus's carbon end up in the sky while Earth's carbon ended up safely in the rock? What did Earth do, or have, that Venus did not, to file its carbon away and keep its sky thin and survivable for billions of years? To feel how strange the carbon bookkeeping really is, hold a single image in your mind. The white cliffs that stand along some coastlines, the pale stone that builds cathedrals and lines, quarry walls, the chalk a teacher once dragged across a board, are all made of carbonate, and carbonate is built from carbon that used to be in the air. Every one of those white cliffs is, in a real sense, a piece of Earth's former atmosphere turned to stone. The shells of countless tiny sea creatures falling to the ocean floor over hundreds of millions of years pulled carbon dioxide out of the sky and locked it into rock, building entire mountain ranges out of buried air. When you look at a chalk hillside, you are looking at a greenhouse that was disassembled and filed away, gas converted to solid and stacked in layers thicker than skyscrapers. That is where Earth's Venus went. We had the ingredients for a crushing sky, and we turned them into stone hills and white cliffs. The contrast is almost unbearable when you put the two atmospheres side by side as numbers. Earth's entire atmosphere, the whole ocean of air above your head, all the weather and the wind and the breathable sky, weighs a certain amount. The atmosphere of Venus weighs about 90 times more. Strip away that difference and ask where the missing mass went on Earth, and the answer is the rocks. The carbon that would have made our air 90 times heavier is sitting in the ground beneath us, in the limestone and the chalk and the fossil fuels, held there, out of the sky, out of the greenhouse. 2 planets, the same carbon budget, and the entire difference between a thin blue sky and a crushing furnace comes down to the single question of whether that carbon was allowed to stay in the air or got pulled down into stone, which means the whole fate of a world hangs on whatever mechanism does the pulling and on the one thing that mechanism cannot run without. The answer is going to come down to a single substance, the most ordinary substance in your life, the one you are made mostly of and that falls from our sky and fills our seas. Because the thing that lets a planet pull carbon out of its air and lock it into stone, the thing that runs the whole filing system that has kept Earth's sky breathable, depends utterly on the presence of liquid water. And Venus, the bright twin in the evening sky, the world we once imagined covered in warm, shallow seas, has not a single drop of liquid water anywhere on it, not a puddle, not a film, not a trace. Which raises the most haunting question in this entire story, the one the next part of the night belongs to. We have very strong evidence that Venus, long ago, had a great deal of water, perhaps even oceans. So where did all of it go? Part 5. The Ghost of an Ocean. Venus is bone dry today, and yet it is wearing the fingerprints of a great deal of water it used to have. This is one of those quiet detective stories that science does so well, where a single careful measurement reveals an entire vanished world. The clue is hidden in the hydrogen of the Venusian atmosphere, and to read it, you have to know that hydrogen comes in 2 slightly different versions. The ordinary kind has a single particle in its nucleus and is very light. The other kind, called deuterium, carries an extra particle, a neutron, which makes each atom of it about twice as heavy. Deuterium is sometimes called heavy hydrogen, and it is rare. Both kinds turn up in water, because water is made of hydrogen and oxygen, so any ocean is a mix of mostly ordinary water and a tiny trace of heavier water built from deuterium. Here is why that matters. When a planet loses its water to space, it does not lose both kinds equally. The process works like a sieve that sorts by weight. Water high in the atmosphere gets broken apart by sunlight, and the freed hydrogen, being the lightest thing there is, can drift up and escape the planet's gravity entirely, leaking away into space. But the lighter, ordinary hydrogen escapes more easily than the heavier deuterium, because it is easier to lift the light thing than the heavy thing. So as a planet bleeds its water away over time, the ordinary hydrogen leaves faster, and the heavy deuterium gets left behind, concentrating in whatever water remains. The longer and harder a planet loses water, the more lopsided that ratio becomes. The leftover air ends up enriched in deuterium, stamped with a signature that says, plainly, a lot of water used to be here, and most of it escaped. When our spacecraft measured the hydrogen in the atmosphere of Venus, they found it enriched in deuterium by roughly 150 times compared to the ratio we see in Earth's oceans. 150 times. That is not a subtle anomaly. That is a planet wearing the unmistakable mark of catastrophic water loss, a chemical scar left by an ocean's worth of hydrogen that drifted away into space across the ages. The dry, cracked, lead-melting surface of Venus is, in effect, standing on the evidence of its own former wetness. The water is gone, but the proof that it was here is written into every breath of the remaining air. How much water are we talking about? The honest answer is that we cannot reconstruct the exact amount from the deuterium ratio alone, because it depends on how the loss unfolded, but the estimates point to something serious. Enough water, plausibly, to have covered the planet in a global layer tens of meters thick, and in some scenarios far more than that, enough to have formed genuine oceans. Set that image against the Venus we met a few minutes ago, the dim orange furnace where the toughest machines we build last 2 hours. The same planet, long ago, may have had water pooling on its surface, not as vapor, not as trace humidity, but as liquid, sitting in basins, catching the light of a younger sun. This is where the story stops being merely interesting and starts, at least for me, to ache a little. Because if Venus had liquid water on its surface, then Venus, the bright evil twin, the symbol of a dead world, may once have been blue. Picture it. A second blue world, right next door, in the same neighborhood as Earth, with clouds, with rain falling from those clouds, with shorelines and shallow seas and the slow weather of a living planet. There is a serious scientific case, built by climate modelers, that Venus could have held on to temperate conditions and surface oceans for a very long time, possibly for 2 or 3 billion years. A span longer than complex life has existed on Earth. In that picture, Venus was not always the furnace. For most of its history, it may have been a habitable world, the sister planet people always dreamed of, and only relatively late in the story did it tip over the edge and burn. I want to be honest with you, because the channel does not do you the disservice of pretending science is more certain than it is. Not every researcher agrees that Venus ever had real oceans. There is a competing picture, taken seriously by serious people, in which Venus was never able to cool down enough to let its water condense into liquid in the first place, in which the planet emerged from its fiery birth already too hot, its water trapped permanently in the sky as vapor, never once falling as rain or pooling as sea. In that version, Venus was never a blue world at all. It was born burning and stayed burning, and the deuterium tells us only that it had water in its air, not that it ever had oceans on its ground. Which of these is true, whether Venus is a lost paradise or a world that was always doomed, is one of the genuinely open questions in planetary science. And it is precisely the question the next generation of spacecraft is being built to answer. We do not yet know whether the planet next door is a corpse or a thing that was stillborn. The disagreement between the two pictures is not a sign that the science is broken. It is a sign of how hard it is to read the history of a planet whose surface has been rewritten and whose air destroys our instruments in hours. The case for a long, wet, habitable Venus comes largely from climate modeling, and one of its more surprising supports is the planet's strange, slow rotation. A world that turns as slowly as Venus, taking longer to spin once than to orbit the Sun, would have very long days and very long nights, and counterintuitively, the models suggest that a slow rotation like that could have produced a thick, protective deck of cloud on the day side that reflected away much of the incoming sunlight, shading the surface and keeping it cool enough for liquid water to persist for a very long time, possibly for 2 or 3 billion years. In that picture, the very sluggishness we think of as one of Venus's oddities may have been the thing that kept it habitable far longer than its closeness to the Sun should have allowed. The opposing picture is colder and is taken just as seriously. In it, the young Venus never got the chance to cool down and let its water rain out into oceans at all. As the planet finished forming, its surface may have been a sea of molten rock, a magma ocean, glowing and liquid, and a surface that hot keeps all the planet's water locked in the sky as vapor, because nothing that hot will permit liquid water to condense. By the time the surface finally cooled, the runaway heating from all that water vapor in the sky may already have set in, so the water never got a window in which to fall and pool. In that version, Venus skipped the blue phase entirely and went straight from molten to furnace, and the deuterium we measure is the fingerprint not of lost oceans, but of an atmosphere that always held its water high and let the sun strip it away from above. The truth may lie somewhere between these, and we genuinely do not yet know which is closer to right. But sit with the first possibility for a moment longer, because of what it would mean. If Venus was once blue, once temperate, once a place where water lay on rock under a sky, then the most important fact about it is not that it is an alien hell, it is that it is not alien at all. It is a version of home that died. And it did not die because it was fundamentally different from Earth, made of the wrong stuff or built on the wrong plan. It died because of a process, a sequence of physical events that took a wet, mild, Earth-like world and converted it, step by step, into the furnace the Venera landers photographed. The dead twin is not a warning about how strange the universe can be. It is a warning about how fragile the familiar can be. And to understand the warning, we have to watch the thing that killed it actually happen, the slow, unstoppable mechanism that turns oceans into sky. We have to watch a planet's water leave the ground for good. Part 6. The day the oceans left the ground. The mechanism that killed Venus has a name, and it is the same name that haunts every conversation about our own planet's future. It is called the runaway greenhouse, and the word runaway is doing a great deal of work because it describes a process that, once it truly starts, feeds on itself and cannot be stopped. To understand it, you have to know one more thing about water, a thing that turns the most harmless substance in your life into the agent of a planet's destruction. Water vapor, the gas form of water, is itself a greenhouse gas. Humid air holds heat better than dry air. Anyone who has felt the difference between a clear desert night, where the warmth flees the moment the sun sets, and a muggy summer night that stays sticky and warm until dawn, has felt water vapor trapping heat. That ordinary fact is the seed of the catastrophe. Now, follow the loop, because the loop is everything. Suppose a world with oceans gets a little warmer, for whatever reason. Warmer oceans evaporate a little faster, which puts more water vapor into the air. But water vapor is a greenhouse gas, so more of it in the air traps more heat, which warms the planet a little further. And a slightly warmer planet evaporates its oceans a little faster still, which adds yet more water vapor, which traps yet more heat. Each turn of the loop feeds the next. Warming drives evaporation, evaporation drives more warming, and the whole thing chases its own tail. On Earth, mercifully, this loop is held in check. Our planet has safety valves. The water vapor condenses into clouds, and clouds are bright and reflect a good deal of sunlight back to space, cooling things down. The vapor falls back out as rain almost as fast as it rises. The loop turns, but it is damped, balanced, kept on a leash by the constant cycling of evaporation and rainfall. For billions of years, Earth's version of this loop has hovered in a stable, livable place. But there is a threshold, a line, beyond which the safety valves can no longer keep up. If the amount of sunlight hitting the planet climbs past a certain critical level, the warming wins. Evaporation outpaces every cooling mechanism the planet has. The oceans begin to pour themselves into the sky faster than the rain can bring them back, and the water vapor accumulates instead of cycling, and each addition warms the planet more, which drives more evaporation, and now there is no stable resting place anywhere in the system. The loop has slipped its leash, it runs away. And it does not stop turning until it reaches the only place it can finally come to rest, which is the point where every drop of liquid water on the planet has been lifted off the surface and into the atmosphere as vapor. The oceans do not partly evaporate. They evaporate completely. The runaway greenhouse does not warm a planet. It boils it dry. Stand on the shore and watch it happen, because this is the moment the twin begins to die. The sun overhead is younger and a little dimmer than ours, but it has been slowly, patiently brightening for hundreds of millions of years, and the world has finally crossed the line. The sea in front of you is warm, warmer than any sea on Earth, and it is steaming, a haze rising off its surface that does not burn away by afternoon the way morning mist does, but thickens, day after day, week after week, until the sky itself has gone pale and heavy with it. The air grows close and wet and hot, and the heat does not break at night because the water vapor holds it, and the held heat lifts more water off the sea, and the haze climbs higher. The horizon, which used to be a sharp line of distant water, softens and then vanishes into white. The rain that falls cannot keep up with the water rising, and over years and centuries and longer, the sea level does not fall the way a drying lake falls. It surrenders upward, the ocean leaving the ground, not by sinking into it, but by climbing into the sky and refusing to come back down. There is no flood and no fire, only a slow, total, unstoppable evaporation, the seas of a living world, lifting silently into the air until the basins that held them lie empty and cracking under a sky that has swallowed every ocean whole. The thing that makes the runaway so frightening and so different from ordinary warming is that there is no resting place once it begins. Most natural systems have a stable point they return to when you push them, the way a marble in a bowl rolls back to the bottom, no matter how you nudge it. A planet with a working set of safety valves is like that, settling back toward balance after every disturbance. But once the warming crosses the runaway threshold, the bowl flips over and becomes a hill, and the marble that used to roll back now rolls away, faster and faster, with nowhere to stop. The system is no longer self-correcting, it is self-amplifying. Every bit of warming guarantees the next bit, and there is no temperature between the starting point and the bone-dry end where the planet can come to rest. That is what the word runaway truly means. It is not fast warming. It is warming that has lost its brakes entirely, and that cannot stop until every ocean is gone. Stand on that young shore a little longer, because the slowness of it is the part that haunts me. There is no single catastrophic day on Venus, no moment of fire, no sudden boiling. From the ground, in any given lifetime, almost nothing seems to be happening. The sea is a touch warmer than it was. The mornings are a little hazier. The horizon is not quite as crisp as the old stories say it once was. Generation by generation, if there were anyone there to notice, the change would be almost too slow to see. A gradual thickening of the air, a gradual creeping of the heat, a gradual surrender of the water upward into a whitening sky. And yet the direction never once reverses. Every century is a little hotter and a little hazier than the last, the loop turning and turning, patient and unstoppable, until after ages too long for any witness to span, the shore you are standing on is dry, cracked rock, and the sea is a memory held only in the chemistry of the air. The death of an ocean does not arrive. It accumulates. That is what a runaway greenhouse looks like from the inside, and it is the leading explanation for what happened to Venus. The extra sunlight Venus received, sitting one lane closer to the sun than Earth, combined with the sun's slow brightening over billions of years, eventually pushed Venus past that critical threshold. Whether it happened early or late, whether Venus had a long blue youth or only ever had water in its sky, the physics of the ending is the same. The water that was on or in Venus was lifted entirely into the atmosphere, and the planet became wrapped in a thick, hot shroud of water vapor and the carbon dioxide that came with it. The runaway is not a slow warming that you could adapt to or reverse. It is a tipping point, a one-way door. Once a planet crosses the threshold, the outcome is fixed. The oceans are going to the sky, and nothing the planet can do will call them back. And yet, strangely, even at this point, the water is not gone. It has only changed address, moving from the surface to the atmosphere. If the story ended here, Venus would be a hot, wet, cloudy world, drowning in its own evaporated oceans, miserable but still in possession of all its water. That is not what we find. The Venus, we find, is not wet. It is the driest place in the inner solar system, holding barely a trace of water anywhere, its oceans not relocated to the sky but gone, vanished from the planet entirely, leaving behind only that telltale deuterium scar. So the runaway greenhouse, as terrible as it is only the first half of the execution. It lifts the water off the ground. Something else has to finish the job, something that takes that water, now hanging defenseless in the upper atmosphere, and removes it from the planet forever. To see how an ocean does not just leave the ground, but leaves the world, we have to follow that water all the way up, to the very top of the sky, where the sunlight is waiting to tear it apart. Part 7. The point of no return. Once the oceans are in the sky, the sun finishes them off, and it does it with a kind of patience that is almost worse than violence. Water that used to sit safely at the surface, shielded under miles of atmosphere, is now lifted high into the upper air, where there is nothing above it but the raw light of the sun. And up there, the sunlight carries a weapon the lower atmosphere never let through. Ultraviolet light, the same band of sunlight that burns your skin, has enough energy to break a water molecule apart. When an ultraviolet photon strikes a molecule of water high in the atmosphere, it can split it into its pieces, separating the hydrogen from the oxygen. The water stops being water. It is taken apart into its raw atoms, and the most important of those atoms is now free, and it is the lightest thing in the universe. Hydrogen, set loose at the top of the atmosphere, does what the lightest thing always does. It rises, and it keeps rising, and because it is so light, the planet's gravity can barely hold it. It drifts up and away, and escapes into space, leaking off the top of the world and never coming back. This is the sieve I described earlier, the one that sorts hydrogen by weight, and now you can see it working. The ordinary light hydrogen escapes a little faster, the heavy deuterium lingers a little longer, and over the ages, the planet's remaining water grows more and more enriched in deuterium, building toward that 150 times signature we measure today. Every escaping atom of hydrogen is a piece of a former ocean leaving the planet for good. The water is not relocating. It is being dismantled and thrown away, one molecule at a time, by the light of the sun. The oxygen left behind has its own fates, mostly reacting with the rocks of the surface and with other gases, binding into the minerals and the chemistry of the planet, so that it too is removed from the picture. What matters is the net result, and the net result is final. The water of Venus, whether it was oceans or only vapor, was taken up into the sky, torn into atoms, and lost to space. And that is the step that makes the death permanent. A planet can recover from being too warm. It cannot recover from having no water at all, because, as we are about to see, water is the one tool a planet needs to fix itself, and once the water is gone, the tool is gone with it. Here is where the second half of the catastrophe unfolds, and it is the part that builds the crushing sky. Throughout all of this, the volcanoes of Venus kept doing what volcanoes do. They erupted, and like all volcanoes, they breathed out carbon dioxide, the same gas that pours from volcanoes on Earth. On a living planet, that volcanic carbon dioxide does not simply pile up, because the planet has a way of pulling it back out of the air, a recycling system that files the carbon away into stone. But that recycling system, as we will see in detail in a moment, runs entirely on liquid water. It needs rain, it needs oceans, and Venus had just lost every drop. So the carbon dioxide from the volcanoes went up into the sky and stayed there, because there was no longer any rain to wash it down, no longer any ocean to dissolve it, no longer any process to lock it into rock. It accumulated. Eruption after eruption, age after age, the carbon dioxide built up in the atmosphere with nowhere to go, thickening, pressing down harder, trapping more heat, for hundreds of millions of years, until it became the 90 times thicker, 92 times heavier, 465-degree atmosphere that crushed the Venera landers. The timescale of all this is worth holding on to, because it is what makes the loss so complete. The escape of hydrogen is not a sudden venting, like air rushing out of a punctured tire. It is a slow leak, atom by atom, drawn out across hundreds of millions and even billions of years. Each individual molecule of water that gets split and lost is nothing, a vanishing trace. But a planet has an enormous span of time to work with, and over that span the trickle adds up to oceans. This is the patient cruelty of the process. It does not need to be violent to be total. It only needs to be steady and to have time, and a planet has nothing but time. Drop by drop, molecule by molecule, the sky strips the water away and throws it into space, and after long enough, an ocean is simply gone, carried off into the dark one hydrogen atom at a time. There is a grim elegance in how each step disarms the planet for the next. The runaway lifts the water off the ground, which exposes it to the sunlight that destroys it, which removes the water permanently, which kills the thermostat, which lets the volcanic carbon dioxide pile up unopposed, which thickens the greenhouse, which locks in the heat that guarantees the water can never return. It is a sequence that systematically removes every tool the planet might have used to save itself, in the exact order needed to make recovery impossible. By the time the carbon dioxide has finished accumulating into that 90 times thicker sky, there is not a single mechanism left anywhere on the planet capable of reversing the change. The world has not only died, it has destroyed, one by one, every instrument it might have used to come back to life. And it did all of this with nothing more exotic than sunlight, water, rock, and time. So now you can see the full sequence, the whole chain of execution from start to finish, and it is chillingly logical. The sun slowly brightens. The extra heat pushes a warm world past the runaway threshold. The oceans evaporate entirely into the sky. The water vapor rises to the upper atmosphere, where sunlight tears it apart and the hydrogen escapes to space, so the water is not merely moved, but destroyed and lost forever. With the water gone, the planet loses its only means of pulling carbon dioxide back out of the air. And so the volcanic carbon dioxide accumulates, unopposed, across geological time, building the monstrous greenhouse that locks the surface at hundreds of degrees. Each step makes the next one possible. Each step makes the whole thing more irreversible. By the end, you do not have a planet that is too warm. You have a planet that has lost the ability to ever be anything but a furnace again, and that is the cruelest feature of the entire process. It is a one-way door, and the reason it is one way is the loss of the water. Imagine you could somehow reach in and cool Venus back down, shade it from the sun, drop its temperature. It would not become Earth again. It could not. Because the water that would be needed to run its recycling system, to start pulling that mountain of carbon dioxide back out of the sky and burying it in rock, is gone, thrown away into space hundreds of millions of years ago, unrecoverable. The planet has no tool left to fix itself. The carbon dioxide would just sit there in the sky forever, because the only thing that could remove it left the planet long ago. Venus did not just get hot, it burned the one bridge that could have led it back. The death is locked in, sealed by the absence of the most ordinary substance there is. This is the point where the story turns from Venus toward us, because everything we have just traced raises one enormous and obvious question. If this sequence is just physics, if it is a chain of ordinary steps that any sufficiently warm, sufficiently close world can be walked through, then why did it not happen to Earth? Earth has volcanoes breathing out carbon dioxide. Earth sits in the same neighborhood, drinking the light of the same slowly brightening sun. Earth has all the same ingredients that Venus had. And yet Earth's sky is thin and blue and breathable, and has stayed that way for billions of years, while its twin one lane closer became a sealed oven. The difference cannot be the ingredients, because the ingredients are the same. The difference has to be something Earth has, or does, that keeps the carbon in the ground and the water on the surface, and the whole runaway loop on its leash. And that something is the most important machine you have never heard of. Part 8. Why we are still here. Earth runs a thermostat, and it has been running for billions of years, quietly, in the background, with no one tending it, and it is the single reason you are alive to hear this. The thermostat is not a thing you can point to, like a machine in a basement. It is a cycle, a loop of chemistry and geology that connects the air, the rain, the rock, and the slow drift of the continents into one self-correcting system. Scientists call it the carbonate-silicate cycle, which is an unlovely name for the most important safety mechanism on the planet. So let me just call it the thermostat. And let me show you how it holds the temperature of an entire world, steady across spans of time longer than there have been animals. It works like this. Carbon dioxide in the air dissolves into rainwater, making the rain very slightly acidic, the way a faint sourness, far too mild to taste. That mildly acidic rain falls on the rock of the continents and slowly wears it down, dissolving certain minerals in a process called weathering. The dissolved products of that weathering get carried by rivers down to the sea, where living things and chemistry combine them into carbonate, the stuff of limestone and chalk and shells. That carbonate settles to the ocean floor and builds up in thick layers, and over long ages, the drifting of the continents, the slow conveyor of plate tectonics, drags those layers down into the planet's interior, burying the carbon far below, locking it into stone. That is the filing system from the earlier part of the night, the one that put almost all of Earth's carbon into rock instead of sky. Rain pulls carbon from the air, weathering binds it, rivers carry it, the sea stores it, and tectonics buries it. The air is continuously scrubbed of carbon dioxide, and the carbon is filed away in the ground. But the truly beautiful part, the part that makes it a thermostat rather than just a drain, is that it corrects itself. The rate of weathering depends on temperature. When the planet warms up, the chemical weathering of rock speeds up because warm, wet conditions wear rock down faster. Faster weathering pulls carbon dioxide out of the air more quickly, and pulling out carbon dioxide weakens the greenhouse, which cools the planet back down. And when the planet cools, weathering slows, so carbon dioxide from volcanoes builds back up in the air a little, strengthening the greenhouse and warming things back up. Too warm, and the system draws down the carbon dioxide and cools itself. Too cold, and the carbon dioxide accumulates and warms itself. It is a genuine thermostat, a negative feedback that pushes back against change in either direction, and it has kept Earth's surface within the narrow band that allows liquid water for something like 4 billion years, even though, as we will see, the sun has been steadily turning up the heat that entire time. Now, here is the part you must not miss, the hinge that the fate of both worlds swings on. The thermostat has one absolute, non-negotiable requirement. It runs on liquid water. Every single step of it depends on water in its liquid form. Rain is liquid water falling. Weathering is liquid water dissolving rock. Rivers are liquid water carrying. Oceans are liquid water storing. Take away the liquid water, and every step of the thermostat seizes up at once. No rain means no weathering. No weathering means no carbon getting pulled from the air. No oceans means nowhere to store it. The whole self-correcting machine stops dead. And now you can see, with perfect clarity, exactly why Venus and Earth diverged, and exactly how thin the thing that saved us really is. Both planets started with the same ingredients and the same thermostat, but Venus sat one lane closer to the Sun, receiving about twice the sunlight, and as the young Sun brightened, Venus crossed the runaway threshold and lost its liquid water to the sky and then to space. The moment its water was gone, its thermostat died, and with the thermostat dead, the volcanic carbon dioxide piled up unopposed into the crushing furnace we see today. Earth, sitting just a little farther out, stayed below the threshold. It kept its liquid water, and because it kept its water, its thermostat kept running, scrubbing the carbon dioxide out of the sky and burying it in rock, holding the temperature steady, decade after decade, eon after eon, all the way down to the breath you are taking right now. The difference between the living world and the dead one was not size, and not chemistry, and not some built-in flaw. It was whether the water stayed liquid long enough for the thermostat to keep running. Venus lost its water, and its thermostat failed. Earth kept its water, and its thermostat held. That is the whole difference. That is the entire story of why one twin is a garden and the other is an oven. It helps to see what happens to a world that has the water but loses a different piece of the machine, because it shows that the thermostat needs more than just liquid water to run. Consider Mars, the other rocky world in our neighborhood. Mars almost certainly had liquid water on its surface long ago, rivers and lakes and possibly seas, and yet Mars is a frozen, nearly airless desert today, the opposite failure from Venus. Mars did not die by overheating. It died by going cold, and a large part of the reason is that Mars is small. Being small, it cooled quickly inside. Its internal heat engine ran down, and it lost the churning, drifting plate tectonics that on Earth keeps burying carbon and recycling rock. Without that geological conveyor, and with its modest gravity letting much of its air escape to space, Mars could not keep its thermostat running either. One twin of Earth lost its thermostat by losing its water to heat. The other lost its thermostat by losing its internal warmth to size. Earth, alone among the three, kept both the water and the inner heat, and so kept the only working thermostat in the inner solar system. That comparison should make Earth feel less like a safe default and more like a narrow, lucky coincidence of several things going right at once. Our planet is the right size to hold onto its internal heat and keep its plates drifting. It sits at the right distance to keep its water liquid, rather than boiling it away like Venus or freezing it solid like Mars. It has held on to enough gravity to keep its atmosphere from leaking away. Change any one of those, move Earth a little closer to the Sun, or make it a little smaller, or start it with a little less water, and the thermostat might never have run at all, or might have failed long ago. The habitable, temperate, blue world we take for granted is not the normal outcome for a rocky planet. It is the rare one. Of the three rocky worlds in our own immediate neighborhood that might have been gardens, two are graves, and only ours threaded the needle. I find that genuinely sobering, and I want to be careful not to oversell it as a scare, but also not to soften it into something it is not. Earth is not safe because it has less carbon than Venus. Because it does not, the carbon is right here, comparable in amount, simply filed away in the rocks. Earth is not safe because it is made of better material, because it is made of the same material. Earth is safe because of a process, an ongoing, running, self-correcting process that depends utterly on the continued presence of liquid water on its surface. Our safety is not a property we possess. It is a machine that happens to still be running. And a machine that is running is a machine that can, under the right conditions, stop. The thermostat held for 4 billion years against a slowly brightening sun. The question that should be forming in your mind, the question that turns this from ancient history into something that touches us, is what happens to that thermostat when the sun does not stop brightening? Because it has not stopped. It is brighter today than it was when the dinosaurs lived, brighter than when the first life appeared, and it is going to go on getting brighter, and Earth's thermostat, faithful as it has been, is fighting a rising tide that it cannot push back against forever. Part 9. The sun is getting brighter. The sun is not a fixed flame, and this is the fact that turns Venus from a story about the past into a story about the future. We tend to think of the sun as a constant, the one thing in the sky you can count on never changing, the same yellow light your grandparents saw and your grandchildren will see. Over a human lifetime, that is true enough, but over the lifetime of a planet, the sun is slowly, relentlessly getting brighter. When the sun was born, about 4.5 billion years ago, it was noticeably dimmer than it is now, something like 30% fainter. Across the ages since, it has brightened steadily, and it is brighter today than it was when the first dinosaurs walked, brighter than when the first life stirred in the seas, and it is not finished. The sun will go on brightening by roughly 1% every 100 million years or so, roughly 10% every billion years, for as long as it shines. The reason is buried in the sun's core, in the nuclear fusion that powers it. As the sun fuses hydrogen into helium in its center, the core slowly grows denser and a hotter core burns brighter. It is an unavoidable consequence of how the sun makes its light, written into the physics of the star itself, and there is nothing that can slow it or stop it. The light that feeds Earth is on a slow, permanent rise. And this raises an obvious problem, one that puzzled scientists for years. If the sun was 30% dimmer in the distant past, the early Earth should have been frozen solid, a ball of ice far too cold for the liquid water and early life we know existed back then. Yet it was not frozen. It had liquid oceans and living things under that faint young sun. How did the early Earth stay warm under a dim sun, and how has it avoided overheating as the sun brightened since? The answer, of course, is the thermostat. The same carbonate-silicate cycle that buries our carbon has been quietly adjusting the dial the entire time. Under the faint young sun, the thermostat kept more carbon dioxide in the air, a thicker greenhouse blanket to make up for the weaker sunlight and keep the planet warm. As the sun brightened over billions of years, the thermostat responded by drawing more and more carbon dioxide out of the air, thinning the blanket to compensate for the strengthening light, holding the temperature roughly steady the whole way. The slow decline of carbon dioxide across Earth's long history is the fingerprint of the thermostat doing its job, letting out the greenhouse a little at a time to balance a sun that would not stop turning up. For 4 billion years, the dial has been turning, and the thermostat has kept pace, and Earth has stayed livable as a result. It is one of the great quiet triumphs of our planet, a balancing act of staggering duration that no one designed and no one maintains. But a thermostat that works by removing carbon dioxide from the air has a limit, and the limit is the thing that dooms us. There is only so much carbon dioxide to remove. The thermostat keeps cooling the planet by drawing the greenhouse gas down, but eventually it draws it down so far that there is almost none left to remove, and at that point the thermostat runs out of room. It has turned the dial as far as the dial will go, and the sun, indifferent, keeps brightening. Once the carbon dioxide can be drawn down no further, and the sunlight keeps climbing, the temperature finally begins to rise, and there is no longer any thermostat left to stop it. The safety mechanism that held for 4 billion years simply runs out of slack. The best estimates put this turning point somewhere around 1 billion to 1.5 billion years from now. At that point, rising sunlight will begin to push Earth toward the same moist, then runaway, greenhouse that took Venus, regardless of anything anyone does or does not do, because it is driven by the sun itself. The faint young sun puzzle is worth sitting with, because it is one of the quiet proofs that the thermostat is real and not just a comforting story. If you take the sun's known brightening and run the clock backward, the early Earth, billions of years ago, received so much less sunlight that a simple calculation says its oceans should have been frozen solid for much of its early history. Yet the geological record is clear that they were not frozen. There were liquid oceans and living things on the early Earth, under a sun far too dim, by the simple math to allow them. The puzzle stumped scientists for a long time, and the resolution is the thermostat. The early Earth held a much thicker blanket of carbon dioxide in its air, a stronger greenhouse to make up for the weaker sun, and as the sun brightened, the thermostat slowly let that blanket out, drawing the carbon dioxide down to keep the temperature steady. The fact that Earth stayed livable across billions of years of a steadily strengthening sun is not luck. It is the signature of a control system that has been working the whole time, turning the dial in the exact direction needed to cancel out the changing star. But a control system that works by spending down a finite resource cannot work forever, and that is the trap we are walking toward. The thermostat keeps the planet cool by removing carbon dioxide from the air, and the more the sun brightens, the more it must remove. Run that forward, and you reach a point, perhaps 1 billion years from now, where the thermostat has drawn the carbon dioxide down so far that there is almost none left to remove, and yet the sun is still climbing. At that point, the dial is turned as far as it will go, and the safety mechanism that protected Earth for 4 billion years simply runs out of room. There is a further cruelty buried in it too. Long before the oceans boil, the falling carbon dioxide will drop so low that the plants which depend on it for photosynthesis begin to starve, so the green world may quietly wind down even before the heat finishes the job. The end does not come because the thermostat fails at its task. It comes because the thermostat succeeds right up until the moment it has nothing left to give. Walk out onto that far future Earth and see it for yourself, because it is the most honest picture of what the title really means. The sun overhead is larger and whiter and fiercer than the one you know, and the day is hot in a way no summer has ever been hot. The thermostat has run out of carbon dioxide to draw down, and the temperature has been climbing for ages, and the oceans have been shrinking, slowly, over millions of years, the coastlines crawling inward, the shallow seas drying to salt flats, the great basins becoming wide, cracked plains. What is left of the ocean is smaller now, a warm and shrinking remnant, and it is steaming the way the young seas of Venus once steamed, the haze rising off it and not coming back, the water climbing into a sky that is going pale and heavy with vapor. The thermostat is dead because the rain can no longer keep up, and without the rain the carbon is no longer being buried, and the same loop that ran away on Venus billions of years ago is beginning to turn. Here, on the world that was ours, the last sea lifts silently into the sky, and Earth crosses the exact threshold its twin crossed long ago, and becomes in time another furnace under another thick and crushing sky. That is not a metaphor, and it is not a worst case, and it is not something we are doing. It is simply the future, written into the sun, scheduled and unavoidable, the literal sense in which Venus is what Earth will become. Our planet has an expiration date, and it was set not by us, but by the star that feeds us, the same star whose slow brightening doomed Venus, and whose slow brightening will one day doom us in exactly the same way. The habitability of Earth was never a permanent fact. It was always on loan, granted by a thermostat with a limited supply of slack, against a sun that would eventually overwhelm it. We happen to live in the long, comfortable middle of that loan, billions of years in, with perhaps 1 billion or more still to run. But the ending is real, and it is Venus, and nothing can be done about that particular ending. The dead twin in the evening sky is not just a corpse from the past. It is a photograph of our own distant future, developed early, and yet, knowing that the true ending is 1 billion years away and beyond our reach, there is a different and far more immediate question folded into the title, the part that says it is already starting. Because, while the sun's version of this is slow and certain and untouchable, there is a faster, smaller version of the same physics that is unfolding right now, on a clock measured not in billions of years but in centuries, and that one does have our fingerprints on it. To talk about that honestly, without exaggeration and without false comfort, we have to be very careful about what the Venus story does and does not tell us about the present. Because the most irresponsible thing I could do is tell you Earth is about to become Venus next century. And the second most irresponsible thing I could do is tell you the planet next door has nothing to teach us about the air we are changing right now. Part 10. And it's already starting. There are 2 clocks ticking in this story, and almost all the confusion about Venus and Earth comes from mixing them up. The first clock is the slow one, the solar clock, measured in billions of years, on which the brightening sun guarantees that Earth eventually becomes Venus no matter what anyone does. We just walk through that one, and there is nothing to be done about it. The second clock is the fast one, the human clock, measured in decades and centuries, on which we ourselves are changing the composition of the atmosphere by digging up carbon and putting it into the sky. These two clocks involve the same underlying physics, the greenhouse effect, the same gas, carbon dioxide, but they run at wildly different speeds and reach wildly different destinations. And to talk about the title honestly, I have to separate them cleanly because the popular version smashes them together and gets the science badly wrong. Let me start with the reassuring half, because it is true and it matters. Burning every drop of oil, every seam of coal, every pocket of gas that human beings can reach will not turn Earth into Venus. It cannot. The numbers simply do not allow it. To build a Venusian sky, you need to put something like 90 times Earth's entire atmosphere worth of carbon dioxide into the air, and there is nowhere near enough accessible carbon in all the fossil fuels on the planet to do that. The runaway greenhouse, the true one, the kind that boils the oceans into space, requires a level of sunlight or a level of greenhouse gas that human emissions come nowhere close to reaching. Earth sits comfortably outside the runaway threshold for now, held there by its distance from the sun and by that thermostat still doing its work. There is no plausible amount of fossil fuel burning that flips Earth into a 465-degree furnace. Anyone who tells you we are about to literally become Venus this century is misreading the physics, and the misreading is not subtle. I should be fair and note that the boundaries here have been argued at the edges. The climate scientist, James Hansen, one of the most prominent voices in the field, has raised a provocative worst-case idea he called the Venus syndrome, suggesting that, in an extreme scenario, burning the dirtiest and most abundant fuels might in principle push the climate further than the standard models allow. It is taken seriously enough to mention, but it sits at the far outer edge of the scientific conversation, and it is not the consensus. The broad agreement among the world's climate scientists, summarized in report after report, is that human emissions cause severe, dangerous, civilization-straining warming without triggering a literal runaway to Venusian conditions. The honest scientific picture is not Earth becoming Venus. It is Earth becoming considerably hotter and more hostile to the particular climate our civilization was built around, which is plenty serious on its own without the furnace. So in what sense is it already starting? Here is the sense, and it is the one I think actually matters, because it is real, and it survives all the honesty I just applied. Remember what the whole second half of this story was about. Earth is livable because its thermostat spent hundreds of millions of years pulling carbon out of the sky and burying it in the ground, filing it away into coal and oil and limestone, thinning the greenhouse blanket to a survivable layer. That buried carbon is the reason our sky is thin and not thick, breathable and not crushing. And what are fossil fuels? They are precisely that buried carbon. Coal and oil and gas are the filed away carbon of ancient life and ancient air, the exact deposits the thermostat spent eons removing from the atmosphere to keep the planet cool. When we dig them up and burn them, we are doing something genuinely new in the history of the planet. We are running the thermostat in reverse. We are taking carbon the planet spent hundreds of millions of years moving from the sky into the ground, and we are moving it, in a few short centuries, from the ground back into the sky. That is the real meaning of it is already starting, and you can hold it without any exaggeration at all. We are nudging the planet in the exact direction Venus travelled. Not far enough to reach where Venus arrived, not remotely, but unmistakably in that direction, and faster than any natural process has ever moved carbon in that direction before. Venus is the proof of concept for where that direction ultimately leads, the worked example sitting right next door of what it looks like when a planet's carbon ends up in its sky instead of its rock. The lesson Venus offers is not you are about to become me. The lesson is the thing keeping you livable is which way your carbon is moving, and you have just started moving yours the wrong way. The direction is the warning, even though the destination is out of our reach. There is something almost poetic, in a dark way, about what fossil fuels actually are, and it is worth saying plainly because it makes the whole picture click into place. Coal is the buried remains of ancient forests. Oil and gas are the buried remains of ancient marine life. All of it is carbon that living things pulled out of the ancient atmosphere using sunlight and that then got buried and pressed into the ground before it could return to the air. In other words, fossil fuels are a portion of the very carbon the thermostat filed away. They are pages torn out of the planet's long project of thinning its own greenhouse. The reason there is so much energy in them is precisely that they represent millions of years of sunlight captured and stored. And when we burn them, we release not only that stored energy, but also the stored carbon, sending it back up into the sky the planet spent so long pulling it down from. We are, quite literally, unfiling the carbon, opening the drawers the thermostat closed, and tipping their contents back into the air. The speed is the part that has no precedent. The thermostat moves carbon on geological time, over hundreds of thousands and millions of years, slow enough that the rest of the planet can adjust as it goes. We are moving it on the timescale of a few human lifetimes. We are taking carbon that took hundreds of millions of years to bury and returning a meaningful fraction of it to the sky in a couple of centuries, which is, in planetary terms, an instant. The thermostat is still running, still trying to pull that carbon back down, but it's weathering and burial work on a clock thousands of times slower than the rate at which we are adding to the air, so it cannot keep pace. This is the real meaning of the warning, stripped of all exaggeration. We are not going to make Venus, but we are running, briefly and locally, the same kind of process that made Venus, in the opposite direction the planet has spent its whole life pushing, and faster than anything in its history. And the direction matters enormously, even though we cannot complete the journey because of where we actually live. We do not live across the whole range, from frozen to furnace. We live in a thin, narrow band of conditions that the thermostat has held steady for a very long time, a band our crops and our coastlines and our cities and our entire civilization are quietly built around. You do not have to move a planet all the way to Venus to cause profound trouble. You only have to nudge it a little way out of the narrow band its life is tuned to. Venus is the dramatic, total, billion-year version, the whole length of the road travelled to its end. What we are doing is a small step down the first stretch of that same road, and the reason to look hard at Venus is not because we are about to arrive there, but because it shows us, with perfect and brutal clarity, which direction the road runs and what kind of place it leads toward. The dead twin is not our forecast, it is our compass, and the needle is pointing at the one thing we have started, just barely, to do to our own sky. Having been that careful and that honest, I do not want to leave Venus as merely a lesson, a cautionary diagram with our name written under it, because the planet itself is still genuinely mysterious, and still, against all odds, may not be entirely dead. There is one more strange thing about Venus that we have not touched, a place on that murderous world where the conditions are, improbably, almost gentle, and where the question of whether anything could possibly survive has refused, for decades, to go quietly away. Part 11. The world still hiding things. There is one place on Venus where the planet stops trying to kill you, and it is not on the ground at all. It is high up, roughly 30 to 40 miles above the surface, in the middle of those endless clouds. Down at the surface, the temperature is hundreds of degrees, and the pressure would crush a submarine. But as you rise through the thick atmosphere, both of those drop, the way they would if you climbed a mountain, and somewhere up in the cloud layer, they pass through a band where conditions become, of all things, almost mild. At around that altitude, the temperature falls to somewhere between the freezing point of water and a warm afternoon, and the pressure drops to about the same as the air pressure at Earth's own surface. In that narrow layer, suspended high above the furnace, you would not be crushed and you would not be cooked. It is the closest thing to Earth-like conditions anywhere in the solar system beyond Earth itself, and it exists in the sky of the deadliest planet we know. Drift there for a moment, because it is one of the strangest places imaginable. You are floating in a thick golden haze, lit by that same sourceless amber light, with no ground visible below and no clear sky above, just an endless, luminous fog stretching in every direction. The air around you is the temperature of a mild day and presses as gently as the air in your room, and you are moving fast, faster than you can feel, because the entire cloud layer of Venus is racing around the planet far quicker than the planet itself turns beneath it, a phenomenon called super-rotation that no one fully understands. The winds up here circle the whole world in about 4 Earth days, carrying you in a great silent loop around the planet again and again. Below you, unseen, lies the crushing furnace. Above you, beyond the haze, lies the black of space, and you hang in the one thin slice between them, where the numbers, against all reason, briefly allow for comfort. There is just one problem, and it is a serious one. The clouds you are floating in are not water. They are droplets of concentrated sulfuric acid, and they would dissolve you as surely as the surface would crush you, only more slowly. And yet that improbable temperate layer is the reason a genuinely startling idea refuses to die. The idea that something might live in the clouds of Venus. It sounds absurd against everything we have said, but the logic is not crazy. If Venus was once a wet, temperate world with surface life, and if that world dried and burned over a long time, then as the surface became uninhabitable, the last refuge for any microbial life would have been upward into that mild cloud layer, the final place on the whole planet where the temperature and pressure still permitted living chemistry. It is at least conceivable that some hardy remnant clings on up there, riding the acid clouds, the survivors of a world that died beneath them. In 2020, that speculation collided with a real and contested observation. A team of astronomers announced that they had detected a gas called phosphine in the clouds of Venus. On Earth, phosphine is interesting because it is strongly associated with life, produced by certain microbes, and not easily made by ordinary planetary chemistry. The claim that it was present in the Venusian clouds set off a wave of excitement and argument, because if it was really there, and if there was really no non-living way to produce it, then it would be a hint, only a hint, of something alive in that high acid haze. But the result has been fiercely disputed ever since. Other researchers reanalyzed the data and argued the signal was weaker than claimed or absent, or better explained by sulfur dioxide, an ordinary Venusian gas, masquerading as phosphine in the measurements. The honest status today is unresolved and leaning skeptical. The phosphine may not be there at all, but the episode did something useful. It reminded everyone that for all our certainty about the furnace below, we genuinely do not know what is happening in the clouds above, and we have barely begun to look. The phosphine episode is worth understanding a little more fully, because it is a small lesson in how science actually behaves when it brushes up against the possibility of life. When the detection was announced, the careful version of the claim was never that life had been found. It was that a gas had been spotted which, on Earth, is hard to make without life, and which no one had a confident non-living explanation for in the conditions of Venus. That is a much smaller and more honest claim, and even it turned out to be shaky. Within months, other teams went through the same data and the same telescopes, and could not all agree the signal was even there, with some arguing it was an artifact or a misread fingerprint of ordinary sulfur dioxide, the common gas of the Venusian clouds. The scientific community did not rush to declare life. It argued, picked the result apart, demanded better data, and largely talked itself back into caution. Whatever the truth about the phosphine, the episode was the opposite of a cover-up. It was the slow, public, skeptical machinery of science doing exactly what it is supposed to do. And yet the question would not fully close, because the cloud layer remains genuinely possible as a refuge, and we have so little data that honest scientists cannot rule it out. That is the strange position Venus leaves us in. We are certain about the furnace at the bottom, and almost entirely ignorant about the haze in the middle. We have never flown an instrument through that temperate cloud band designed to look carefully for the chemistry of life. The handful of probes that passed through it were built for other purposes decades ago. So the most provocative question about Venus, whether anything at all still lives in the one survivable layer of a dead world, sits there unanswered not because we have looked and found nothing, but because we have barely looked at all. It is a reminder that even our nearest planetary neighbour, the one we have known about since before history, is still mostly unexplored in the ways that matter most. That is, the real state of Venus. It is not a solved planet. It is a world we have touched for a total of a few hours, mapped only through radar, and still cannot answer the most basic questions about. We do not know for certain whether it ever had oceans. We do not know exactly when or how it tipped into the runaway. We do not know whether its surface is volcanically alive right now, though recent re-examinations of old radar data have found hints of a vent that seems to have changed shape between two passes in the early 1990s, suggesting active volcanoes. We do not know what drives the super-rotation of its clouds, or why it spins backward, slower than any other planet, with a day longer than its year. The dead twin is still keeping secrets, and the most important secret of all is the one that matters for us, the question of whether it was ever alive. This is why, after decades of relative neglect, Venus is finally getting a wave of new missions, what some scientists have started calling the Decade of Venus. There is a planned probe called Da Vinci, designed to fall slowly through the atmosphere the way the old Venera landers did, but this time tasting the air all the way down, measuring its chemistry with modern instruments, and crucially, pinning down that deuterium signature precisely enough to tell us how much water Venus really lost and when. There are orbiters, one called Veritas and a European mission called ENVISION, built to map the surface and the interior in far finer detail than ever before, to read the planet's geological history and settle whether it once had the conditions for oceans. These missions have wrestled with delays and budget troubles, and the timelines have slipped toward the early 2030s and beyond. But the intent is clear. We are finally going back to the twin with the tools to ask it the right question. Within our lifetimes, we may actually learn whether the planet next door was once a blue and living world that died, or whether it was born burning and never knew water at all. And the answer, either way, will tell us something profound about how rare or how fragile a world like ours really is. Part 12. The Mirror Next Door. So let me gather the whole night into a single thought, and then let you rest with it. We began with the bright twin in the evening sky, the gentle sister world everyone expected to be a softer Earth, and we found instead the hottest, most hostile surface in the solar system, a furnace under a beautiful lid. But the furnace turned out not to be the strange part. The strange part is how it got that way. Venus did not become a hell because it was built wrong. It became a hell because it was built almost exactly like us, and then a slow, ordinary, understandable process walked it step by step from something possibly Earth-like to something murderous. The closeness to the sun, the brightening light, the lost water, the dead thermostat, the carbon piling unopposed into the sky. None of it required a flaw. All of it required only physics, and a little less distance from the same star we orbit. When you understand that, the word twin stops being a label and becomes a mirror. Venus is not a curiosity off to the side, a strange neighbor with nothing to say about us. It is the one place in the universe that shows us, in physical detail, written across a whole planet, one real and specific way that a world like Earth can end. We talk about the death of planets in the abstract, billions of years from now, hard to picture and easy to dismiss. Venus makes it concrete. It is the worked example, the answer at the back of the book, the photograph of an ending developed early and hung in our own sky where we can see it every clear evening. And the ending it shows us is, on the long clock of the sun, genuinely our own. In a billion years or so, give or take, the brightening sun will overwhelm Earth's thermostat. The oceans will climb into the sky and be torn apart and lost, and Earth will follow its twin into the furnace. That part is not a warning. It is simply the future, and there is a strange peace in that, the same peace there is in knowing that all things, even worlds, are temporary. But the nearer lesson is the one to carry with you, and it rests entirely on that quiet machine most people have never heard of. Everything that keeps Earth livable, everything that holds our sky thin and our oceans liquid and our temperature in the narrow band our lives are tuned to, rests on a thermostat that runs only as long as there is liquid water to run it, and that keeps our carbon filed safely in the ground. Venus is what happens when that carbon ends up in the sky instead. And the single new thing our species has started to do, in just the last couple of centuries, is to take some of that carefully buried carbon and move it back into the air, running the thermostat, just slightly, in reverse. We cannot turn Earth into Venus. The honest physics is clear about that. But Venus tells us, with total clarity, which direction that road runs and what kind of country lies at the end of it, and it is worth knowing the direction even when you cannot reach the destination. I keep returning, in my own mind, to how ordinary the whole thing is, and I think that is the part worth carrying to sleep. There is nothing exotic in the story of how Venus died. There is no cosmic accident, no wandering asteroid, no nearby explosion, no special bad luck. There is only sunlight, water, carbon dioxide, rock, and time, the most common ingredients in the inner solar system, arranged in a slightly different order than they were arranged here. A little more sunlight, a little less distance, and the same physics that keeps Earth gentle ran the other way and built a furnace. The horror of Venus, if it is a horror, is not how strange it is how familiar. It is the realization that the line between a living world and a dead one is not drawn by some rare and dramatic event, but by quiet, ordinary processes that are running right now on both planets, and that simply settled into a kinder balance on one of them than on the other. And that ordinariness is exactly why the thermostat is the thing I would have you remember out of all of this. It asks nothing of us, takes no notice of us, and has held the temperature of the whole planet steady for 4 billion years, using nothing but rain and rock and the slow drift of continents. Almost no one has heard of it. Almost no one thinks about it. And yet every harvest, every coastline, every comfortable afternoon you have ever had was underwritten by that silent machine doing its work in the background, filing our carbon into stone and holding our sky thin enough to breathe and clear enough to see through. It runs only as long as the oceans last, and it can only file the carbon if we are not, at the same time, digging it back up faster than it can work. That is not a reason for fear. It is a reason for a particular kind of attention, the attention you give to something precious that you had not realized was doing so much so quietly for so long. So the next time you are outside on a clear evening and you see that one brilliant point of light low in the west after sunset, or high in the east before dawn, steady and calm, and brighter than anything else in the sky, stop for a moment and really look at it. You are not looking at a star, and you are not looking at a symbol of love, whatever the old names say. You are looking at a world almost exactly the size of the one under your feet, made of the same rock, born beside us from the same cloud, around the same sun. You are looking at what may once have been a second blue world, with oceans and clouds and rain, a sister that may have been alive when our own planet was young. And you are looking at the ghost of those oceans now, a planet wearing the chemical scar of the seas it lost, sealed under a sky of acid and crushing carbon, holding a single steady temperature hot enough to melt lead from pole to pole through a night that lasts for weeks. That light is the most valuable thing in the sky, precisely because of what it is. It is the only place we have ever found that shows us, in advance and in full, one true way a living world can die, and lets us read the whole story of it without having to live through it ourselves. It is a warning we were lucky enough to be handed for free, hanging in plain sight every clear night of our lives. Most warnings come too late to do anything with. This one came 1 billion years early, and whether we ever learn to read it well, whether the knowledge of how a twin of Earth became a furnace ever changes the small, slow things we do to our own sky, the planet will go on shining there regardless, patient and bright and silent, the ghost of an ocean and the photograph of a future, waiting in the west for anyone who knows how to look. We do not yet know whether Venus was ever truly alive. The machines we are finally sending back may tell us, within our own lifetimes, whether the bright twin was a paradise that was lost or a world that never had a chance. But either answer leaves the deepest fact untouched. Two worlds began the same and ended a garden and a grave, separated by nothing more than a little distance, a little water, and the patient turning of a thermostat that one of them kept and the other lost. The universe does not promise a living world that it will stay alive. It only lends the conditions, for a while, and asks nothing in return but that we notice, while we can, how rare and how fragile the loan really is. Rest easy tonight. The thermostat is still running. The oceans are still here. And the bright twin in the evening sky is still keeping its secrets, a little less every year, for as long as we keep looking up.